Singapore is running out of space.
There are more developments now. It's harder to find land.
Now the little red dot is being re-engineered for the 21st century.
Nobody has done it before. This is the only job that allows you to work on a smart city project in Singapore.
We are going from about 350 megawatts of solar to 2 gigawatts of solar, and that's a huge jump.
New mega projects using state-of-the-art technologies to dig deep.
I did not believe the space-saving part until I saw it with my own eyes.
This is what engineering is all about.
Harness the power of the sun.
It's kind of new for Singapore to have solar panels on water.
And automate its ports.
I can't imagine we will be developing a 60-plus berth.
All designed to find more space to allow Singapore to flourish.
Tuas Megaport will be a very significant game changer.
This is a journey into Singapore's Tomorrow City. It's 6 a.m. and already the construction site at Singapore's western extremity is abuzz with activity. Today, engineers will tow this massive concrete block from land to sea. It's called a caisson, and it's the most critical part of Singapore's port of the future. It is one of 227 concrete structures that will be installed over the next 8 years to form the largest of 4 wharves or land fingers, with over 8-kilometre-long seawalls each. This is Tuas Megaport. The port construction is a 25-year undertaking across 4 different phases. Phase 1 has already reclaimed 294 hectares of land, and Phase 2 has to reclaim and build 387 hectares. The last 2 phases are under construction, with the entire port expected to be fully open by 2040. Since 2015, different parts have been built and scheduled for staggered openings. Now, in 2021, the very first part of the port is set to open up to container processes. The Tuas Megaport will be fully automated, using drones, key cranes and driverless vehicles to cut down the turnaround time of the world's biggest container ships. In the 21st century, international trade is driven by high-tech logistics. The ultimate goal is for Tuas to be able to handle double the capacity of what all Singapore's current 5 ports can manage.
After this land has been reclaimed, the container terminals infrastructure will be built.
But as Singapore extends its global reach across the world's oceans, the city-state's need for fresh water is rising year on year. Water for its growing population and industries. And that's where the problem of space kicks in. To manage water, Singapore needs space, and that's in short supply. Inland, huge new projects are harvesting the waters of the sea. And here at Tuas, engineers are creating new land on a huge scale. At the new port, planners refer to the building of land fingers that are separated by sea passages to optimize large shipping workflows.
The reclamation of Tuas Port Phase 1 started in 2015, and it takes about 5 to 6 years to complete the reclamation. And Tuas Phase 2 commenced in 2018, and it takes another 6 more years to finish the reclamation.
For project director Eugene Koo, this is his favorite place to monitor progress of the huge construction site.
This is the best spot that I like because it gives me a view of the overall progress of the site. At one time, I can see all the activities of the site from this angle.
The new port will take 2 decades to complete, covering an area equivalent to over 1,300 stadium fields. The key to reclaiming land is the Caisson, a 28-meter-high watertight concrete box that is built on land, then towed out to sea. Caissons are like Lego blocks that are submerged and linked together to build the seawalls of each of the 4 land fingers of the new port. They are crucial to the land reclamation process at Tuas.
Over here, you can look at the installed caissons. We have installed 67 caissons already, and that's close to maybe 2/3 of our length of the Finger 2 reclamation.
Each caisson weighs 15,000 tons. That's equivalent to about 8,000 cars stacked together. Cast from poured concrete, each caisson is 10 stories high. Another 136 of these concrete giants must be cast and towed out to sea before the seawall can be completed. Any disruption of the cycle will have a knock-on effect on the construction schedule. As planners discovered in 2020, when the COVID-19 virus raced through the foreign workers' dormitories, and work at Tuas came to a grinding halt. Since that crisis, the engineer in charge of the Caisson construction process, D.W. Kim, has strained every sinew to catch up. Every month, he must deliver 8 completed caissons. So 2,000 workers have been kept busy around the clock for months.
Caisson casting yard is something like a factory.
Inside the Caisson factory, 2 of the giant structures are at different stages of production. Number 95 is almost ready to be towed out to sea, where it will be sunk to form part of the quay wall. Work on number 92 is just beginning, with the casting of the base slab. This slab functions as the casting form, so it's vital that the engineers check for weak spots.
We have a monitoring system, so micro management of each activity. Each step has many activities, so each activities are under supervision and monitoring to check each step progress.
The team soon discovers a problem. There is a defect in the base slab. Defects usually occur when the concrete dries unevenly. It must be repaired, and fast. Defects can only be prevented by making sure the concrete gets poured evenly into the slab. To do this, the workers insert a vibrating rod to stir the concrete constantly as it gets poured into the casting mold of the slip form. All this checking and repairing are essential works. Caissons must be watertight. If seawater, which is highly corrosive, penetrates any cracks in the base, these will widen over time and weaken the entire structure.
I think the vibration is not enough. That's why this kind of defect is coming.
The team uses a probe to check whether the concrete has hardened evenly. Kim and his team are able to repair the base of number 95. The team at number 92 is ready to cast the tower. Caissons are more complicated than they look on the outside. This giant gantry acts as a cast or slip form for the tower. Inside the tower is a concrete box-shaped framework, a clever way of reducing the weight of the structure without compromising its strength. The site workers build up the box structure layer by layer inside the gantry.
interior level is good. The setting is also good, and the entry gap is also good. So most important thing is we casting even level, the same level concrete casting.
At the Tuas site, work on the caissons continues day and night. As each level is poured and checked, the platform moves up another level. One caisson in its slip form is so heavy that the engineers have to use 36 sets of hydraulic jacks to push the platform up as more concrete goes in. Just one of these sets can lift 1,500 tons, around the weight of 11 blue whales.
If this hydraulic jack is not gripping properly, then it may cause slippery issue. Meaning all this slip-form structure can collapse.
Each set of jacks must work in perfect unison. The head operator has to make sure the weight of the caisson is distributed evenly amongst all the jacks.
So every jack operator should understand operating the operation room and downside the middle deck working also.
Yeah, all understand.
Anyway, every hour please monitor, okay?
There's one more step in the construction process for number 92.
That's why we will apply the sealant to the caisson. So this sealant will function like coating the caisson to prevent the corrosion.
Silane will protect the caisson, but it is hazardous to work with because it is a toxic chemical. In the past, spraying was done by workers in cages that ascended the sides of the huge structure. Today, the engineers at Tuas have come up with a safer method, which is to apply the chemical across the full breadth of the caisson. They have also automated the process with an unmanned spraying mechanism.
So this frame positioned on top of the caisson, the worker from the ground will operate the sealant. So just press the button, then the nozzle will hoist down. At the same time, application, rotating and apply the sealant.
This new process covers even the corners that are the most difficult to reach. This innovation won the team a Health Safety Award in 2020. When each caisson is completed, it will be moved onto a floating dock, ready to be pushed out to sea to take its place in the seawall. As the new port reaches out caisson by caisson into the ocean, ready to embrace the future, Singapore gears up to resolve more challenges inland with its water supply. Singapore's new port development demonstrates confidence in the growth and prosperity of the city in the 21st century. But expansion comes at a cost. Growth will put huge pressure on the small island's resources, with a higher demand for fresh water supplies.
Singapore's water demand is currently at 430 mgd, or million gallons per day. That's equivalent to 782 Olympic-sized swimming pools. And by 2060, that amount of water is projected to almost double. And the second challenge is those that is brought by climate change. Climate change introduced a lot of uncertainties and also extreme weather patterns. Too little rain will cause drought, and we can't really rely on the local catchment and imported water.
So the Public Utilities Board, or PUB, is finding innovative new ways to treat rain and seawater as well as used water, which can be recycled. All part of the government's plan to make the island a global hydro hub. Since 2006, it has committed $479 million to foster cutting-edge technologies in the environment and water industry. Regardless, the problem remains. Singapore is not short of water, but of space.
Here in Singapore, every year we receive 234 centimeters of rain, so it's more than enough for the population. But the problem is we have such a high population in such a small land area. That creates the challenge. So that's why we're developing technologies like ocean desalination to help provide enough water for the large population.
At the Nanyang Water and Environment Research Institute, Professor Shane Snyder and his team are involved in a radical experiment to increase the efficiency of an age-old seawater filtration method, otherwise known as desalination. Their method can also help in the treatment of rain and used water.
So capturing the rainwater takes two things. It takes the surface area, but also the depth. And we just don't have enough surface area and depth to capture all the water. Especially when the water comes, or rain comes more heavy at certain times of the year, we have no choice but to release it to the sea.
There are already 17 reservoirs that capture and store rainwater in Singapore. They are connected by a network of canals and rivers. Altogether, these take up about 473 square kilometers, or 2/3 the size of the island. Catchment above ground is clearly not the solution in the long term. So Singapore's water planners have designed something new. These joggers may not realize that one of the most innovative solutions to Singapore's water problem in recent years lies right beneath their feet. The state-of-the-art Keppel Marina East desalination plant. It's constructed almost entirely underground across 2.8 hectares. That's more than 2 football fields combined. And it is designed to fit into the landscape of the East Coast Park. The plant is state-of-the-art, such that it can switch from desalinating seawater to treating rainfall. Both processes can take place in the same desalination plant. The plant can treat about 30 million gallons a day, up to 7% of Singapore's daily water needs.
It's a dual-mode desalination plant, the first one in Singapore, and it was developed in-house. So what it does is it is able to switch between treating freshwater and seawater. So during the abundant rainfall, it will take freshwater from Marina Reservoir.
So there's different ways to remove salt from water for desalination. But today we mainly use membrane technologies. These are highly specialized membranes that use a high amount of pressure to push the freshwater through and leave the salt behind.
Seawater is, of course, an almost limitless resource. But the biggest problem about desalination is that it requires a lot of power. The pressure that has to be artificially created to push the water through the filtration system is equal to the pressure 650 meters deep down in the ocean.
So the largest reason is energy. Because to push water through a membrane at any reasonable speed, it'll take a lot of pressure, and pressurizing the water takes very large electrical pumps. So that electrical energy component is extremely large. The membranes and other infrastructure are also costly, but it's really energy at the end of the day. So the more salt the water has, the higher the amount of pressure to push the water through the membrane at a given speed. And that's part of the problem. So the Keppel facility is a dual mode. So if there's an ample amount of fresh water, it's able to process that first and save a lot of energy, while still producing a very high quality of water.
This makes the dual-mode desalination plant the most flexible operation model for water processing in Singapore to date.
So, Pang Chan,
Yep. We have been on reservoir mode, right?
Yep.
We are going to switch, right?
Yep. We're currently on reservoir mode. We're going to switch to the seawater mode. So now we'll do the final round of the check. If everything okay, we'll start the reservoir water switch to seawater mode.
Okay, good.
Okay.
But even a state-of-the-art plant like this doesn't solve the problem of energy in the long term. And the switchover process is complex, requiring several hours. Because seawater carries lots of salt and rainwater carries other minerals.
The reservoir typically have a lower conductivity or salt content compared to seawater. So if you want to move to seawater, you require it to be slowly increased up to the certain level of the conductivity or the salt content before the next process unit can start.
But what might just revolutionize desalination in the next few decades to come isn't the power source, but a critical material required in the process itself. It is the membrane that is used for all types of water treatment that turns it into freshwater supplies. As Singapore's economy grows and becomes ever more globalized, huge pressure will be placed on its water supplies for industries and homes. Water demand in Singapore is currently about 430 million gallons a day, enough to fill 782 Olympic-sized swimming pools, with residential homes consuming 45% of it. The PUB is investing vast resources to treat the water that falls on Singapore from the sky and the reservoirs of the ocean. But existing technologies of water treatment consume a lot of power. So the search is on for new innovations to make desalination more energy efficient. For some scientists, the key to innovation is the design of the membranes that are used to treat water. The process of treatment filters the water to remove unwanted substances like minerals, salts, or certain bacteria. In his lab at the Nanyang Water and Environment Research Institute, Professor Snyder is experimenting with ceramic membranes that will challenge the traditional ones made from plastic. A membrane is made up of several layers of filters that allow water to pass through but keep unwanted particles out. Thin coatings of chemical substances can be applied to the different filter layers. Such coatings can emphasize the filtration effect for various uses of the membrane. In this case, a special coating makes it even easier for water to pass through the membrane during the desalination process. Professor Snyder's tests showed that ceramic membranes also require less maintenance than plastic membranes.
Okay, so what we have here is a bench scale setup to test ceramic membranes. These membranes are actually made of aluminum oxide and some other metals, so it feels like a coffee cup, but the membranes are extremely resilient. But this is brand new, so we want to test it, we want to understand its resilience, we want to understand how it removes viruses, even the coronavirus, pollutants, etc. So we build a small system like this. The membrane goes inside this pressure vessel, and then it allows us to put different chemical combinations, different water qualities, and to evaluate how well this membrane is performing and how long does this membrane last.
Professor Snyder's experimental membrane is still in the research phase and has not yet been tested at the industrial level. Next door, Professor Wang Rong is working on another radical solution that's also membrane-related. The idea her team is pursuing is inspired by nature. Specifically, a tiny protein called aquaporin, which forms the plumbing system of cells in fish, plants, and humans. Aquaporins move and filter water through cells and are naturally efficient.
Aquaporin water channel can be found in our body. Our kidney have the aquaporin and balance our body's water level. Yeah, so this is a natural protein, but highly permeable to water, highly reject the salts. So people think about, can we incorporate this one into the thin film to improve our membrane's performance? We want to increase the water production. We hope water can go through the membranes with a high flow rate. So we developed a new type of the membranes in hope that this membrane have a much higher water flux, water permeability. How is today's experiment?
Yeah.
It's okay.
Yeah, all the parameters we can see from here.
Okay.
The new membrane design is already showing promise for letting water travel through more quickly and easily, with less pressure needed. This is referred to as water permeability.
The water permeability double, so that's the big improvement. 100% improvement in water permeability. That's a quite exciting result, right? We learn from the nature. Nature create a perfect water filtration system and create this water channel protein. We learn from the nature by making use of these proteins put into our synthetic system.
With this high-tech coating layer of the new membranes, the team is able to adapt to different water treatment needs, from removing salts from seawater to mineral substances from rainwater, and even recycling used water. The membranes can be equipped with different filter and coating layers so that the same design can be pushed into different treatment systems, like the one at the Keppel Marina East desalination plant.
So the way we plan to do it is for the membrane to be of the industrial size so that it can easily be plugged into the existing plants. It can be easily retrofitted without having too much works to do it. It's like plug and play kind of thing.
The team's next milestone will be to prove that success in the lab can be replicated in the real world.
And we want to make sure that in the future, even though there are increasing water demand, there are rising of energy demand, as well as uncertainties with the weather patterns, we are still able to deliver water sustainably and at an affordable cost.
But water demand isn't just on the rise for household taps. The non-domestic sector, with industrial manufacturing at its heart, now consumes 55% of the current water supply.
So the predictions are that the amount of water required for our industries could begin to be a larger amount than we use in our communities or our homes. So for Singapore, this means we have to be even more innovative. Because again, we have not enough land space, not enough catchments. We are continually looking at ways to expand that. But the ocean desalination is one of those key technologies that allow us to increase our freshwater even if we cannot increase the catchment size.
But planners will have to be mindful of the potential impact on the environment.
We need to look very carefully that we aren't moving from one problem in water and creating another problem in our energy demands or our CO2 output. So I think we absolutely need to look holistically at our systems and build the systems that make the most sense with the lowest environmental footprint.
While Singapore pushes on to innovate its freshwater supply systems through new tech, it is also reaching out into the waters beyond its furthest shores to ensure that Singapore's future will be guaranteed in the century to come. For more than 700 years, the lifeblood of Singapore depended on its port. In the 19th century, Singapore grew to rival other great port cities like Sydney, Bombay, and Hong Kong. Today, the volume of shipping and trade pouring in and out of Singapore continues to expand at a spectacular rate, with an 8% increase in vessel arrivals between 2011 to 2019, and close to 140,000 ships arriving in Singapore in 2019 alone. So the biggest task ahead is to innovate Singapore's ports. This comes with its own set of challenges. The most daunting of all? Limited space. The plan is to build one megaport to rule them all. Tuas is in the midst of a 4-phase, 25-year construction project that will be able to manage up to 2 times the total amount of cargo that's being handled now by 2040. The key is the reclaimed land that will raise the port right from the oceans and expand Singapore's land area by more than 1,300 hectares. It is also ramping up the logistics, with plans to become the biggest automated and AI-powered port in the world. But aside from limited space, the biggest challenge for Tuas planners yet is to imagine the needs of the ships in the coming decades, and even the 22nd century. The Tuas land reclamation is extending long pieces of land into the sea. The total 4 so-called land fingers, which are built across 4 construction phases, need to be able to accommodate the ships of the future.
So we're actually planning the port for the future mega vessels. So the design catered for the ships that are longer and ships that are deeper. And as a result of that, we have designed our fingers to be more than 3 kilometers long to be able to cater for future vessels up to a draft of 21 meters. And so with a deep water port and linear berths, then we will be able to accommodate ships of all sizes, be it small sizes and up to the larger sizes. We actually optimize it by making sure that the wharf length for ships to berth is the longest possible, and that's about 3.7 being the longest at our phase 2.
Land finger number 2 has been completed for the partial opening of the port in 2021. So the logistics tests are in full swing. But what's going to drive and manage the operations of the megaport isn't the people. Everything is going to be remotely controlled. The key to automation in Singapore's tomorrow port is artificial intelligence, AI. These automated systems will all be controlled by a kind of superbrain. Automation is already taking place in other modern international ports. But Tuas will take this to the next level. From the very minute the container ship docks. Processing the giant container ships of the future will be a spectacular ballet of automation. As soon as a ship is berthed, these green automated cranes, known as double trolley key cranes, get to work. Right here alone, on land finger number 2, are a total of 24 cranes. They are equipped with sensors that can detect the position and proximity of containers. Each crane, which weighs a crushing 2,300 tons, has a lifting height of 55 meters and outreach of 73 meters, and will move to the designated ship once the information is put into the system. But these new machines still need to learn how to process the data from the sensors and scanners. The team has to test the machines in thousands of scenarios to make sure the system works, rain or shine, in all situations. At land finger number 2, the team has spent the last 4 months trying to make this a reality. Today, engineer Wei Xiang and his team are running the final tests of the automatic cranes.
Crane 3. May I know who is on crane 3?
I think on top level 2 computer.
Okay. Help me check with them. What are they doing on this testing?
Now they do this well first about 5 minutes. Later they hand over.
Okay. Can you all proceed first? We are approaching crane 3. So we have various scanner on the crane and a camera system so that the crane can detect the container as well as the truck or AGV.
These massive cranes are capable of lifting up to 65 tons at a time.
Once the crane are fully commissioned, this whole area will be a fully automated area where all this will be fenced up.
The testing process is like a flight simulator used to train pilots. Testing out different scenarios, but with the real machines in a real location.
So this platform, we have a number of safety features being installed above to ensure that when there are laden containers moving in, no human should be in the trolley path. So this to ensure that the whole flow is safe.
But on the off chance that a human has to enter this automated zone, it's vital that the machines are able to detect human movement and pause their actions in time to prevent potential workplace accidents and injuries. Be it the monster cranes or the AGV trucks, the automated vehicles. Everything works fine. The crane detects the presence of the worker and halts. The team proceeds to the next test, moving the container from the automated crane onto the AGV.
Right now it's doing we are simulating offloading of container from vessel, means from the seaside, okay, onto lashing platform and then finally onto AGV. AGV need to be in position, okay, before secondary spreader can move up into the AGV lane.
A problem pops up. The AGV stopped at the wrong spot.
The AGV is not in position, it stopped halfway.
Yeah, there is some system problem. Let me check with the guys.
The AGV uses a digital compass, or GPS, for map data and its sensors to analyze its position on the ground at any point in time. Based on its position, the supervisory system will create and send down the optimum routes for each AGV. The AGV will then track the routes to reach its destination.
Okay, it's a marker on the ground that tells the AGV what coordinate or what axis it is moving. And there is a centralized system that is controlling or telling AGV where to move. Okay, so they will plan out the route, okay, from point A to point B and to point C.
But it seems that the AGV is confused. In a real-world scenario, operations at land finger number 2 would have to be shut down. So now, the engineers have to work out what's gone wrong.
Okay, 4065.769.
No, it's talking to.
The coordinate, right? Right now they are saying that it's 3 decimal.
Right, then. Well, the AGV not in position yet. They key in the wrong coordinates. That's what happens when you have manual. That's why the automated system, once it has all the coordinates, it will not be wrong.
At last, the AGV moves into the correct position. Next, Wei Xiang tests how the double trolley key crane will react if the AGV is out of alignment. The AGV is not in the right place, so the crane should immediately stop moving. But it doesn't. This is yet another new problem.
So right now, AGV is obviously not in position, but the crane still moves up with the container. Okay, so let's go down and troubleshoot to see what's wrong.
In the real world, a glitch like this could damage the container and its contents. Wei Xiang suspects the culprit is the system that is supposed to read and analyze the ground position and proximity to other machines.
Okay, the container need to bring back to the lashing platform, then spreader lower down to the ground for us to check the FLS. Allen key 小响队有没有？
我知道有没有。
不知道有没有？你问他们一下看。 那我们看这个天位这边，这个的位置是 OK 的，这个看起来没有问题，所以这个也是没问题。
Finally, he spots the problem. The laser that was used for the alignment process failed. It didn't scan the surroundings properly.
Okay, one of the laser, okay, is maybe not tightened properly. Yeah, so we will go there and found that it's not tightened properly. We will try to adjust it and tighten it.
Now that he's sorted the laser, Wei Xiang runs through the full test sequence one more time.
OK，
你看现在吊具已经对齐这个箱子了，对齐这个箱子就能够成功的着箱。扫描已经完成，alignment 也已经完成了。好，成功的着箱了。
OK， 所以现在放得到，现在就代表我们的这个测试案例成功了。
好，这个 job 就算完成了。
OK， 好的，很好。
Over the next few months, the team will continue to test the system to the max, to iron out any wrinkles that might disrupt operations, or in the worst-case scenario, endanger lives. While the infrastructure team adapts the new AI system to real-world challenges on land finger number 2, the seawall construction at land finger number 3 continues, one caisson at a time. Today, the team is ready to finally move caisson number 95 out to the ocean, to be positioned in the sea wall. This is the most crucial part of the caisson assembly line. The huge concrete giant is pushed on steel tracks onto a floating dock. Each caisson weighs 15,000 tons, and this is just one of 227 of them. 2 boats are involved in the sea operation. A tugboat in front is pulling the caisson, and a boat behind is pushing it towards the installation site.
7 a.m. we started towing the caisson, and then arrived around 10 a.m. It takes around 3 hours.
The boats tow the dock out to sea to bring the caisson to the exact position above the ocean floor. When it gets submerged, it has to connect to the quay wall. This step has been carefully planned by the engineers using GPS positioning. As the boats reach the installation site, they slow down.
Oh, so what is the progress now?
Now, water pump installation for caisson sinking.
Okay, then we will install the 8 pump, and then will take around 2 hours, right?
Yes, sir.
And then once installation complete, okay, we will start ballasting the caisson, meaning the sink down. Certain level, we will leave around 2 meters, and then we will do the final installation activity. Meaning, using the GPS, we need to monitor the final position. And then we will sink down together with the positioning.
A crane awaits them on another floating dock, which will shift and align the caisson. Now, the tricky operation starts. As the team changes to manual tugging and pulling of the caisson at the surface to match the GPS position underwater. The workers have to manually move the 10-story high caisson right down to the exact millimeter.
Because our tolerance is only 50 mm, so micro adjustment is required.
As soon as the GPS coordinates for the caisson position are matched, the caisson is sunk. The team gradually floods the box-structured interior of the caisson while they continue to manually check its position. Meter by meter, the caisson sinks down to the ocean floor. Once it gets fully sunk, it is linked up to the rest of the already installed caissons.
Okay, once installation finished, then we will call our consultant to get the joint survey for final position of caisson. And then we will repeat this activity.
Finally, number 95 has become a part of the Tuas Megaport's land finger number 3 quay wall. After a few days, engineers perform a final check on the GPS position. With number 95 submerged, the production line continues relentlessly without a break. As the Tuas Megaport grows into the sea, expanding Singapore's land area and its global impact as a port nation and economy hub of the future. The new challenges to manage space and resources herald the way to the Little Red Dot's future with the need for mega projects. From reimagining the port of the future and channeling its water resources to constructing an underground highway for its waste and transforming landmass into solar energy plants. These will push the limits of present-day technology and accommodate the needs of a nation not just for decades, but centuries to come, while leading the way for others as a global economic powerhouse. But this is only the beginning. Using cutting-edge technology, automation, and innovative designs, Singapore is making the future of its people the main agenda of today. Welcome to Tomorrow City.